Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to compute gross efficiency and develop torque of a three-phase induction motor for a particular value of slip when parameters of its exact equivalent circuit are given. The following are the per-phase parameters of the equivalent circuit of a 415 volt 50 Hz 6-pole 3-phase star-connected induction motor. Stator impedance equals to 0.2 plus J times 0.5 ohm. Magnetizing reactance equals to 25 ohm. Core loss resistance equals to 150 ohm and equivalent rotor impedance referred to the stator equals to 0.3 plus J times 0.7 ohm. Using exact equivalent circuit, we have to calculate rotor speed, stator current and its power factor, rotor current, mechanical power developed and power input, developed torque and gross efficiency at slip of 4%. Let us first write down the given data. Standstill rotor impedance per phase referred to the stator Z2S dash equals to R2 dash plus JX2S dash equals to 0.3 plus J times 0.7 ohm. For a particular slip S, rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 4%, that is equal to 0.04 per unit. Therefore, Z2 dash equals to 0.3 by 0.04 plus J times 0.7 ohm. That gives us 7.5 plus J times 0.7 ohm. This may be written in polar form as 7.5326 ohm at an angle 5.332 degree. For the shunt branch, given resistance per phase representing core losses RC equals to 150 ohm and magnetizing reactance per phase XM equals to 25 ohm. Let us now calculate RC plus JXM. Using values we get 150 plus J times 25 ohm. This may be written in polar form as 152.069 ohm at an angle 9.4623 degree. Now we shall determine shunt impedance per phase. Z0 equals to RC parallel with JXM, that is equal to RC into JXM divided by RC plus JXM. Using values we get 150 into 25 at an angle 90 degree divided by 152.069 at an angle 9.4623 degree. That gives us 24.66 ohm at an angle 80.5377 degree. This may be written in Cartesian form as 4.0541 plus J times 24.3245 ohm. Now we shall calculate Z0 plus Z2 dash. Using values we get 11.5541 plus J times 25.0245 ohm. This may be written in polar form as 27.563 ohm at an angle 65.2167 degree. Now we shall calculate equivalent impedance per phase. ZEQ equals to Z0 parallel with Z2 dash that is equal to Z0 into Z2 dash divided by Z0 plus Z2 dash. Using values we get 24.66 at an angle 80.5377 degree into 7.5326 at an angle 5.332 degree divided by 27.563 at an angle 65.2167 degree. That gives us 6.7392 ohm at an angle 20.653 degree. Given line-to-line terminal voltage VL equals to 415 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 415 divided by root 3, that gives us 239.6 volt. Given stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.2 plus J times 0.5 ohm. We have obtained equivalent impedance per phase ZEQ equals to 6.7392 ohm at an angle 20.653 degree. This may be written in Cartesian form as 6.3061 plus J times 2.377 ohm. Let us now calculate total input impedance per phase. Zin equals to Z1 plus ZEQ. Using values we get 6.5061 plus J times 2.877 ohm. This may be written in polar form as 7.1138 ohm at an angle 23.855 degree. Let us now calculate stator current per phase. I1 equals to ET divided by Zin. Taking terminal voltage per phase ET as reference, we get I1 equals to 239.6 at an angle 0 degree divided by 7.1138 at an angle 23.855 degree. That gives us 33.68 ampere at an angle minus 23.855 degree. Now we shall determine rotor current per phase referred to stator side. I2 dash equals to Z0 divided by Z0 plus Z2 dash into I1. We have obtained shunt impedance per phase Z0 equals to 24.66 ohm at an angle 80.5377 degree and Z0 plus Z2 dash equals to 27.563 ohm at an angle 65.2167 degree. Using values we get I2 dash equals to 24.66 at an angle 80.5377 degree divided by 27.563 at an angle 65.2167 degree into 33.68 at an angle minus 23.855 degree. That gives us 30.1327 ampere at an angle minus 8.534 degree. In polar form, stator current per phase I1 equals to I1 at an angle minus phi1 equals to 33.68 ampere at an angle minus 23.855 degree. For star-connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 23.855 degree, that gives us 0.9146 lagging. For three-phase induction motor, total power input P in equals to root 3 times PL into I1 cos phi 1. Using values we get root 3 into 415 into 33.68 into 0.9146, which is approximately equal to 22,142 watts. Now we shall calculate total air gap power. Pg equals to 3 times I2 dash square into real part of Z2 dash. We have obtained rotor current per phase referred to the stator I2 dash equals to 30.1327 ampere and rotor impedance per phase referred to the stator Z2 dash equals to 7.5 plus J times 0.7 ohm. Therefore, Pg equals to 3 into 30.1327 square into 7.5, which is approximately equal to 20,429.5 watt. Now we shall determine total mechanical power developed. Pm equals to 1 minus S times Pg. Given slip S equals to 0.04 per unit. Therefore, Pm equals to 1 minus 0.04 into 20,429.5, which is approximately equal to 19,612 watts. Given number of poles of the machine P equals to 6 and supply frequency F equals to 50 Hz. Let us now determine synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 6, that gives us 1000 revolutions per minute. Now we shall calculate rotor speed. Nr equals to 1 minus S times Ns. Given slip S equals to 0.04 per unit. Therefore, Nr equals to 1 minus 0.04 into 1000, that gives us 960 revolutions per minute. Now we shall determine gross efficiency of the motor. Eta G equals to Pm divided by Pin. We have obtained total power input Pin equals to 22,142 watts and total mechanical power developed Pm equals to 19,612 watts. Therefore, eta G equals to 19,612 divided by 22,142. That gives us 0.8857 per unit or 88.57%. Expression for developed torque. Td equals to Pm divided by 2 pi into Nr by 6T. Using values we get 19,612 divided by 2 pi into 960 by 6T, which is approximately equal to 195 Newton meter. Now we shall learn how to determine equivalent rotor current I2 dash using Thevenin's theorem. For this purpose, we shall remove the load, that is the equivalent rotor impedance per phase Z2 dash from this circuit. Now, the open circuit voltage as seen from terminals A and B gives us Thevenin's voltage. Given stator impedance per phase Z1 equals to 0.2 plus J times 0.5 ohm. This may be written in polar form as 0.5385 ohm at an angle 68.2 degree. We have determined rotor impedance per phase referred to the stator Z2 dash equals to 7.5 plus J times 0.7 ohm, that is equal to 7.5326 ohm at an angle 5.332 degree, and shunt impedance per phase Z0 equals to 4.0541 plus J times 24.3245 ohm, that is equal to 24.66 ohm at an angle 80.5377 degree. Now we shall calculate Z0 plus Z1 using values we get 4.2541 plus J times 24.8245 ohm, that is equal to 25.1864 ohm at an angle 80.276 degree. Let us now determine Thevenin's voltage. V Thevenin equals to Z0 into I, that is equal to Z0 into ET divided by Z0 plus Z1. Using values we get 24.66 at an angle 80.5377 degree into 239.6 at an angle 0 degree divided by 25.1864 at an angle 80.276 degree. That gives us 234.6 volt at an angle 0.2617 degree. To determine Thevenin's impedance, let us short circuit the voltage source. Now the impedance as seen from terminals A and B gives us Thevenin's impedance. Z Thevenin equals to Z0 parallel with Z1, that is equal to Z0 into Z1 divided by Z0 plus Z1. Using values we get 24.66 at an angle 80.5377 degree into 0.5385 at an angle 68.2 degree divided by 25.1864 at an angle 80.276 degree. That gives us 0.527245 ohm at an angle 68.4617 degree. This may be written in Cartesian form as 0.193564 plus J times 0.49 ohm. Now we shall compute Z Thevenin plus Z2 dash. Using values we get 7.693564 plus J times 1.19 ohm. This may be written in polar form as 7.785 ohm at an angle 8.7925 degree. We have obtained Thevenin's voltage V Thevenin equals to 234.6 volt at an angle 0.2617 degree, and Thevenin's impedance Z Thevenin equals to 0.527245 ohm at an angle 68.4617 degree. Let us draw the Thevenin's equivalent circuit as seen from terminals A and B. Now we shall connect the load, that is the equivalent rotor impedance per phase Z2 dash, back to this circuit. Now we shall compute the load current or the rotor current per phase referred to stator side. I2 dash equals to IL equals to V Thevenin divided by Z Thevenin plus ZL, or V Thevenin divided by Z Thevenin plus Z2 dash. We have obtained Z Thevenin plus Z2 dash equals to 7.785 ohm at an angle 8.7925 degree. Therefore, I2 dash equals to 234.6 at an angle 0.2617 degree divided by 7.785 at an angle 8.7925 degree. That gives us 30.135 ampere at an angle minus 8.5308 degree. Now we shall calculate induced EMF per phase. E1 equals to Z2 dash into I2 dash. We have determined rotor impedance per phase. Refer to the stator. Z2 dash equals to 7.5326 ohm at an angle 5.332 degree. Therefore, E1 equals to 7.5326 at an angle 5.332 degree into 30.135 at an angle minus 8.5308 degree. That gives us 227 volts at an angle minus 3.1988 degree. We have obtained induced EMF per phase E1 equals to 227 volts at an angle minus 3.1988 degree. In Cartesian form, this may be written as 226.6463 minus J times 12.6667 volt. Now we shall compute stator current per phase. I1 equals to Et minus E1 divided by Z1. We have computed stator impedance per phase. Z1 equals to 0.5385 ohm at an angle 68.2 degree. Using values we get I1 equals to 239.6 minus of 226.6463 minus J times 12.6667 divided by 0.5385 at an angle 68.2 degree. That gives us 18.1175 at an angle 44.3582 degree divided by 0.5385 at an angle 68.2 degree. That is equal to 33.6444 ampere at an angle minus 23.8418 degree. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine gross efficiency and develop torque of a three-phase induction motor for a particular value of slip when parameters of its exact equivalent circuit are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.